Welcome, students. Today, we delve into an intriguing problem from LeetCode, specifically problem 141, titled Linked List Cycle. This challenge invites us to analyze the structure of a linked list to determine whether it contains a cycle. Imagine a linked list, an elegant structure composed of nodes, each containing a value and a pointer to the next node. In some cases, a node may point back to a previous node, creating a loop. Your task is to identify this phenomenon. For instance, consider the input where the head of the list is represented by the values 3, 2, 0, 4, with the second node pointing back to the first. In this scenario, we observe that a cycle exists, leading us to conclude with a Boolean output of true. Our objective today is to explore the methods by which we can uncover such cycles within linked lists. Let us embark on this intellectual journey together. The fast and slow pointers technique is a valuable method used to tackle problems in linked lists and sequences. Picture two runners on a track. One runs faster, while the other jogs slowly. By moving at different speeds, they can reveal important relationships in the data structure they traverse. In this technique, we employ two pointers. One moves quickly, often 2 steps at a time, while the other moves slowly, taking only 1 step. This difference in speed allows us to efficiently determine if a cycle exists in a linked list. If the fast pointer catches up to the slow pointer, we have detected a cycle. This method is efficient, operating in linear time, ON, and requiring only constant space, O1. It's perfect for memory-sensitive situations. By using this straightforward yet powerful approach, we can gain insights into the structure of our data with minimal resources, whether we're checking for cycles or determining midpoints. In this example, we're using the fast and slow pointers technique to find the middle of a linked list. First, we initialize 2 pointers, the slow pointer and the fast pointer, both starting at the head of the list. The slow pointer moves 1 step at a time, while the fast pointer jumps 2 steps ahead. Now, as we traverse the linked list, we continue moving the slow pointer forward by 1 node, while the fast pointer moves forward by 2 nodes. This creates a situation where the fast pointer, moving faster, will eventually catch up with the slow pointer if the list has an even number of elements. The key point here is that when the fast pointer reaches the end of the list, the slow pointer will be positioned right at the middle. Finally, we return the slow pointer, which points to the middle node of the linked list. This technique is efficient and elegant, allowing us to find the middle without needing to count the total number of nodes first. Cycle detection algorithms are essential tools used to identify cycles in data structures like graphs. A cycle occurs when a path leads back to the same point, forming a loop. This concept is vital in both directed and undirected graphs. For example, in directed graphs, the edges have a specific direction, while in undirected graphs, they don't. Detecting cycles has real-world applications, such as in software development where it helps identify infinite loops that could crash programs. In databases, cycles might reveal redundant or inconsistent data relationships. To find cycles, we often use traversal methods like depth-first search, DFS, or breadth-first search, BFS. These algorithms track visited nodes during traversal. If a node is revisited, we've found a cycle. In directed graphs, we must carefully manage node visitation states, as detecting cycles can be quite nuanced. Understanding these algorithms is fundamental to effectively working with graph structures in computer science. The function you see here is designed to detect a cycle in a directed graph using Floyd's tortoise and hare algorithm. This method is quite efficient for identifying cycles, which can often be tricky to spot. We start by initializing 2 pointers, slow and fast, both set to the first node of the graph. Imagine slow as a tortoise that takes 1 step at a time, while fast is a hare that leaps ahead, taking 2 steps for every one of slow's steps. As we traverse the graph, we move slow to the next node, while fast jumps 2 nodes ahead. The critical moment happens when we check if both pointers meet. If they do, it indicates a cycle exists in the graph. If fast goes out of bounds before they meet, we conclude there is no cycle. This method is efficient and elegant, helping us find cycles without needing extra space. Understanding this algorithm is essential, as cycles can lead to unexpected behaviors in many applications, such as linked lists or graphs. LeetCode problem 141 focuses on detecting a cycle in a linked list. To tackle this, we can use Floyd's cycle detection algorithm, often called the tortoise and hare algorithm. First, we need to define a list node structure, which represents each node in our linked list. Each node contains a value and a reference to the next node. Next, we initialize 2 pointers, slow and fast, both starting at the head of the list. The slow pointer moves 1 step at a time, while the fast pointer moves 2 steps. This way, if there's a cycle, they will eventually meet. As we traverse the list, we continue moving these pointers until fast reaches the end or slow equals fast. If they meet, it indicates a cycle. If we reach the end, there is no cycle. We also cover edge cases like an empty list or a single node list, where a cycle isn't possible. The time complexity for this approach is O(n), and the space complexity is O(1), making it efficient. Finally, we can implement the function that checks for cycles in a linked list using these steps. By following this process, you can effectively determine if a linked list contains a cycle. In this problem, we are tasked with determining whether a singly linked list contains a cycle. A cycle occurs if a node is revisited during traversal, indicating that we can reach a node again after starting from the head. Key constraints include having up to 10,000 nodes, with node values ranging from -100,000 to +100,000. Notably, if the head of the list is null, we can immediately conclude that no cycles exist. Let's explore how we can efficiently solve this problem. The provided Python code tackles LeetCode problem 141, which is about detecting a cycle in a linked list. This algorithm uses Floyd's cycle detection method, often referred to as the tortoise and hare approach. It's designed to determine if a cycle exists while being efficient in both time and space. Here, we have the list node class, which represents each node in the linked list. Each node holds a value, val, and a pointer to the next node, next. The hasCycle function initializes 2 pointers, slow and fast, both starting at the head of the list. Inside the while loop, which runs as long as fast and fast.next are valid, the slow pointer moves 1 step at a time, while the fast pointer jumps 2 steps forward. This difference in speed means that if a cycle exists, the fast pointer will eventually catch up to the slow pointer, leading to the condition if slow equal fast. This method achieves a time complexity of O(n) and a space complexity of O(1), making it very efficient. Using 2 pointers avoids the need for extra memory, enhancing our memory efficiency while keeping the algorithm straightforward and easy to follow. When analyzing the complexity of the linked list cycle problem, we first look at time complexity. The algorithm operates at O(n). This means that in the worst-case scenario, we may need to traverse the entire linked list, visiting all n nodes, particularly if there is no cycle present. Think of it like walking through each room in a long hallway. You won't know if there's a hidden door until you check every room. Next, consider the space complexity, which is O(1). This indicates that the algorithm uses a constant amount of space, regardless of the input size. It only requires a few pointers for traversal, much like needing just a flashlight to navigate through the hallway. There's no need for extra storage or lists, making it efficient in terms of memory usage. Understanding these complexities helps us appreciate how algorithms can be efficient, not just in speed, but also in resource usage.